In this video, I'll be going over everything there is to know about seismic retrofit hardware. That includes nails, bolts, staples, lag screws, different types of shear transfer ties, different types of anchors that hold foundations together, and how the species of wood makes a big difference on how the hardware will perform. Also a big chapter on lag screws, because lag screws that were developed recently by Simpson StrongTie are a real must for seismic retrofitters, and these were not available for quite some time. So we're going to go over all that stuff. It's about half an hour, and you're going to learn a lot. You might want to keep notes, or certainly expect to hit your rewind button quite a few times. It's very, very technical. But if you're getting to do a retrofit on your own, or if you're going to have a contractor do it, or you just want to know more so you can do a better job for yourself, that half hour that you spend here will certainly be worthwhile. So now we're going to be looking at specific gravity. Specific gravity is a measurement of density. So for example, 2 pounds of gold, if you were to throw it in some water, it would sink immediately because it's very dense. You would take 2 pounds of wood and you would throw it in some water and it would float, and that's because it's not very dense relative to the gold. Now, wood has different specific gravities. For example, Douglas fir larch, which is what practically every house is made out of from the mudsill up, is Douglas fir larch, and it has a specific gravity of 0.5. Now the other thing wood we work with is old growth redwood, which is also called close grain redwood, which has a specific gravity of 0.44. And then we also have specific gravity of new growth redwood, which is called open grain, and that's 0.37. So we need to look at all those different types of wood and the specific gravity and see how it impacts the fasteners. That fastener, I mean a bolt, I need a lag screw, I need a nail, it's a staple, anything that connects two pieces of wood together. Now, because shear walls, the plywood, is also dependent on nails, the nails that go into the redwood, we also need to see how that impacts the shear wall itself. So we're going to be looking at all of that. We're going to go, what we're going to do is we're going to go into onto the internet. There's a connection calculator published by the American Wood Council. American Wood Council is a research lab, represents a research lab that does all the tests on wood, and it's extremely important. It's so important that the way the building department reads is that any publication published by the American Wood Council is valid and can be used and approved by the building code. So that's extremely important. I'm going to show you how to use that calculator to determine things that are important to us as seismic retrofitters. So this is a table from the Simpson StrongTie catalog, and it discusses the Simpson URFP foundation anchor, which is used quite extensively in seismic retrofit work. What this table tells us is that in the F1 direction, F1 means parallel to the grain. In other words, if you look at a piece of wood and it has a grain, that's what the growth lines are. And if you're pushing against the piece of wood parallel to the grain, and there's a bolt in it, or in this case a URFP, it can resist 1,530 pounds of earthquake force. Now if we go into a redwood mudsill right here, in this case it's a new growth redwood mudsill, that drops all the way down to 1,180, and that is because of the specific gravity differential. We have gone from 0.50 to 0.37, and that differential in terms of the ability of the bolt of the URFP to resist earthquakes has made a dramatic change. So in our retrofits, we must always look at the type of wood that we're putting our fastener in our bolt or URFP, whatever it happens to be, in order to get accurate values. So we're going to go to the internet now, and I'd like for you to type in American Wood Council Connection Calculator. And when you do that, you'll come up with a page that looks just like this, and this page will enable us to determine the capacity of any type of fastener we want. And we'll use bolts, nails, whatever we want. We'll be able to determine that. And the big thing that makes the difference in terms of capacity that we'll see in a minute is the specific gravity. That's really the determinant, and I'm going to show you how that works. So this is the first page of our calculator. First thing it tells us is we're going to be using the allowable stress design. Now, allowable stress design is simply a way something is looked at. And allowable stress design means how much resistance does the building code allow you to call it. And so if they did tests at the American Wood Council, which is, you know, the agency that does all these tests and figures out all this stuff, if they did some tests and they found out that, say, a bolt failed at 3,000 pounds of earthquake force, and they say, well, we're going to allow you to only call it 1,000 pounds because maybe the bolt steel will be defective, or maybe if it's in some wood, maybe the wood will have a big knot in it, or, you know, laboratories kind of, it's not like a real world, so, you know, we'll just go ahead just to be safe. We will allow it to be called 1,000 even though it has in the test, which is called ultimate load, has actually resisted more than that. So the other thing we're going to be looking at here, this is lateral loading. This is simply earthquake force. That's a sliding motion. We're going to be looking at a bolt. And then we have the loading scenario. In other words, what are we going to be loading? What are we going to be? What two pieces are we going to be attaching to? So in this case, we're going to have a bolt, and then it's going to go into concrete. Now that's called the main member. The main member is the thing that the fastener goes into. So this is the main member here. So what happens is the bolt comes through here, something we call the side member we'll look at in a minute, and then goes into the main member. So this is our setup right here. We've got allowable stress design. That's the system we're using. We're doing a lateral loading, which means it's an earthquake. We're looking at a bolt. And finally, we're going into concrete. So we submit the initial values for that. And now we're going to go in and look at the other things. Again, the main member, that's the thing that we bolt into, is concrete. And we're going to say our bolt goes in. What good wedge anchor is about 4 inches, so we're going to call it wedge anchor depth. The penetration into the concrete is 4 inches. Angle of grain doesn't really matter. We're just going to be using, we're just go straight in. Then we have the type of wood. Now that is a difference. This is a side member. Remember, that's the piece that the bolt goes through. So in that case, we're going through redwood, and we'll go ahead and say that we're going through, let's say it's a house that's fairly new, and we're going to be going through the open grain wood redwood. So that's a new type of redwood. And so let's say we're going through that. That's our side member. And we keep scrolling down, and we don't have to worry about angle of load grain. We don't have to worry about that. Our bolt is 1/2 inch. Let's go ahead and make that 5/8 just for fun. So this is a 5/8 bolt. And this load duration factor, if you're looking at an earthquake, load duration factor means it's very sudden. In other words, the load duration is very sudden, it's very quick. So this is simple. This is simple force. If you're just pushing on it all the time, you can figure out how much a bolt can resist. Or if it's being pushed on very suddenly, like in an earthquake, you can figure out how much force it can resist. And the way you do that is you multiply the whole deal by 1.6. So that is our earthquake load duration factor. So we take all that information and we do our connection calculator, and we find out that it can resist 1,291 pounds. So that's if we go through the new growth redwood. Now let's make a difference here. Let's go ahead and go through some Douglas fir. Let's just figure we've got a Douglas fir Mudsill. It's pressure treated, which is a newer type pressure treated Douglas fir large piece of wood, and same thickness. So let's go ahead and see what happens there. So now we come down and we see it can resist 1,485. So that's about 200 pounds more than what we were looking at before. So we have 1,485 right here. And then again, if we go back to our redwood, we end up with calculate connection. We end up with 1,291. So it's 485, 1,291. So what happened here, all things were equal. The size of the bolt, the concrete, the wood, except the wood. Everything was equal except the wood. And the wood is what has the specific gravity differential. So because one was 0.5 and one was 0.37, we see this dramatic difference in the ability of that hardware to resist earthquakes. So If we go into nails, we'll have the same experience. If we go into staples, we go into screws, we go into anything at all, we will discover the exact same thing about specific gravity. And that's why this is so handy right here, because we can just put in the type of hardware, the type of, the way what it's bolting together, how deep it is, thickness, all that kind of stuff can go into this calculator. So this is probably one of the handiest tools that a retrofitter can have for doing the work that he does. So this same calculator also has a function where it can tell us how much force it takes to pull a nail out of a piece of wood, and this can be very valuable when designing our shear walls. So we're going to go over that right now. These are illustrations of what happens when the plywood on a shear wall fails. The thing we're going to be looking at here is if there's a difference between redwood and Douglas fir in terms of something that will resist that. So here we have, this is our plywood, that yellow right here. The nail is remaining intact, exactly where it should be. So let's say there was an earthquake, everything stayed right where it is. There's absolutely no problem. Here we have nail pullout. And in this case, the plywood has remained, it's still there. The nail and the plywood are connected, but look, it's pulled out of the framing. This is the framing right here. And in this case, we've had complete failure where the nail has pulled through and the nail has pulled out. And, again, in this case and this case, we did have nail pullout, and that is something that we want to avoid if possible. So here we have an actual photograph of it. Here's the, this was the plywood. In this case, it's OSB. Here's a nail here, here's a nail here, and here was a nail here. And it's pulled the nails out. It hasn't pulled out completely, but it certainly, gave that piece of plywood a lot of stress. And this is a partial failure of the shear wall. We can go down and look at this one right here. A very similar situation, except now we have a complete failure, where the nail has pulled out of the framing, and at the same time it's no longer even touching the plywood anymore. It's just pulled out completely. So that is something that we definitely want to avoid. So let's go ahead and see how redwood and Douglas fir compare in terms of their ability to resist that kind of action. So here's our connection calculator, and what we've done here, we are using allowable stress design again. In this case, the connection type we're looking at is withdrawal. So that's withdrawal of the nail. So we have a fastener type as our nail. We're going into Douglas fir. This is the main member. Remember, that's the one you nail into. That's at 3.5 inches. Regular 2x4 is 3.5 inches. And we're using plywood. That's the side member. Remember, that's the part that you nail through. It's 15/32, which is the same as 1/2 inch. That's the way we commonly talk about it. And then it's just a common nail. It's an 8-penny nail. And then we have a low duration factor because of earthquake of 1.6. And so we hit our calculate connection capacity, and we come down here and we end up with 104 nails. So in other words, it would take a carpenter would have to have a hammer, and he's pulling in such a way that at the leverage at the very base where the nail is, you would be able to measure 104 pounds pulling up on it. So let's go ahead and see what happens when we go with old growth redwood. So everything is the same, withdrawal, nail, except the main member is going to be redwood. And we're going to use the old growth redwood because that's what we use when we flush cut mudsills, which is a common technique that we use. So let's go ahead and see what happens now. So here we're getting 75 pounds, and that's that's 25–30% difference in the ability to keep that buckling from happening. And that's a pretty big deal because that's where the shear walls fail. And if we want to make that that connection, that strength of the connection to keep it from pulling out as strong as we possibly can. So anyway, when we're going into redwood, we should probably tighten up our nailing pattern. So exactly how much, you can decide that for yourself, but it should be such that the withdrawal resistance in the redwood mudsill equals that of the withdrawal of the other framing members. So for example, as we just saw, it's about a 30% difference in terms of withdrawal strength between the nail in the redwood and the nail in the Douglas fir. So if you were to put in 1/3 as many nails, that would You know, that would probably be close. But personally, because in the photographs I've seen, the failure into the mudsill is extremely common. That's where it seems like that's where the failures always occur. And so I would say really tighten it up quite a bit. So, you know, get as many nails in there as you can. So if you're going into, you know, if you're 4 inches on center, you know, all overall, you know, go 2 inches on center into the Redwood mudsill. If you're 3 inches on center and you're nailing, go into 1.5 inches on center into the Redwood mudsill. And if you're at 2 inches on center, probably, you know, you might want to go 1.5 inches. You know, you push 1 inch might be pushing it a little bit. So what I would do is when you cut the mudsill, have a section there that, you know, you haven't nailed yet, where that is exposed, and then go ahead and shoot some nails in it. And if it comes out that they don't split, you can go ahead and even go as close as 1 inch. So those are the things to look at. You know, when you go into redwood, you are going into a different specific gravity wood. It does have a different reaction, and one of the big reactions that's different is the nail pullout, and that's what we want to worry about. The shear is also slightly different, but and I guess this would also help a little bit in shear. It would balance it a little better. Now the shear in the redwood would equal the, you know, shear strength of the Douglas fir. But the main thing is we really want to address that pull-out problem. So let's see what happens when you change the thickness of the mudsill. We were just looking at a mudsill that was made out of Douglas fir larch, and the thickness of the sill was 1.5 inches. The bolt is 5/8 of an inch, and the load duration multiplier because of earthquake is 1.6. Now we connect all that together, and of course we get this capacity of 1,485 pounds. Now if we keep everything just the same, but we go ahead and change the thickness, we're going to see what happens. So we come up here and we change this to 3.5 inches, which is what you would normally get for a, you know, that's what you get if your mudsill is made out of that. A lot of times new construction, you're putting in a new sill, you're putting in new concrete, all that. You would end up with a 4x sill very easily. And so we calculate our capacity, and now we're up to almost 2,000 pounds. So what that means is that if we have a shear wall that can resist 550 pounds per linear foot, it can resist 5,500 pounds of force. You divide that by the 1915, and you end up, you only need 3 bolts, and you even have a little bit extra capacity after that. So by knowing that, you can really save a lot of money. Some contractors, what they'll do, they just say, okay, we're putting in a shear wall, and we just, you know, it's 10 feet long, I'll divide by 2, and then I get 5 bolts. But if you really dial in and you get exactly what's needed, you can get a great retrofit, and you can reduce costs, you can make money, and you can be competitive and really give people a great retrofit based on sound science. So right now we're going to take a look and see how specific gravity impacts the strength of our fasteners, such as bolts, nails, shear transfer ties, any hardware you can imagine that goes into wood will be impacted by specific gravity. The first thing we need to be aware of is what the specific gravities are. So for Douglas fir, it's 0.50. And the reason Douglas fir is so important is that that is our baseline. Everything is based on that, in that all the tests that were done on hardware have always been on Douglas fir. And then if you change it to a different type of hardware, I mean a different piece of wood, if you go from Douglas fir to redwood, let's say, you have to use a multiplier. So that you can do a conversion to see what the strength would be in redwood. We mostly use old growth redwood, which is called close grain redwood, or we use open grain redwood, which is your newer stuff, about 1945 on. You can tell because it's only 1.5 inches thick rather than the full 2 inch that you see in the old growth. So these have different specific gravities. So the old growth close grain redwood is 0.44. The new growth redwood is at 0.37. And the way the multiplier is figured out is this: we take the old growth, which is the 0.44 that we have right here, we divide it by the specific gravity of the Douglas fir, and we get 0.88. Same thing for the new growth. We just take the new growth specific gravity of 0.37. divided by the old growth, by the redwood, the Douglas fir, and we get 0.74. So let's see how this works in practice. So we have a 10 penny nail, 1.5" penetration. We've got, it's in Douglas fir, it's 188 pounds of earthquake resistance it provides. And so what we do is we take that, we're going into redwood now, so we go with our redwood multiplier, which is right here. We go 0.88 into 188 pounds, we get 165 pounds. And so what that means is that nail can actually resist 165 pounds when it goes into old growth redwood. So all things being the same, just change one of the pieces of wood to old growth redwood, and then you have a new value. So the same thing if we have a toenail, and it's where it's rated 120. If we multiply it times 0.88, we end up with 106. So this actually has a pretty big impact on bolt capacity. So we're going to take a look at that right now. So here's a 1/2" bolt. Here's an 1.5" sill. That's what you would find in Douglas fir, this is to be your pressure treated wood. You don't see Douglas fir in sills until it's pressure treated, because when you touch wood to concrete, it's got to be treated to keep it from rotting, because redwood is naturally resistant to decay. So pretty much anything, if it's 1.5", it'll be that's the only time we find Douglas fir is when it's pressure treated. Now in the 1.5" sills, we do see a lot of redwood houses built between 1945 and before pressure treated came in. I'm guessing that's about 1975 or so, I'm not really sure. But we'll also see redwood mudsills that are open grain. They're not old growth, they're open grain. The way you tell is if they're only 1.5" thick. So what we have here is we have a bolt in Douglas fir. It will resist 1,037 pounds, but when we go into the open grain redwood, it ends up being 912. So it's very similar. If we have a 1/2" bolt with an MSP, it's 1340. And the reason we can have that is because the original tests were done in Douglas fir. So that's exactly what we have, but we have to make a reduction. We multiply that times our 7.74 and we get this. And you can just go on down the line. Basically everything along here, you multiply it times 0.74 because you're in open grain redwood, and you end up with these numbers right here. Now I wanted to show you this one right here because it shows the impact of the thickness of the wood that the bolt's in. So this is a 3x. Now a 3x naturally that's 2.5 inches rather than 1.5 inches as far as the sill goes, and because of that there's more bolt that is actually touching the wood. So you have 2.5 inches of wood touching the bolt rather than just 1.5 inches, and that has a dramatic impact on the ability for a bolt, for the wood to resist an earthquake. So when the earthquake force is pushing on the bolt, there's 2.5 inches that are pushing on it rather than 1.5 inches. And what that ends up meaning is that the 3x material does not split until it gets to 1,890 pounds. And that's a lot. So in a situation like this, you could actually be building a shear wall. Let's say it's 10 feet long. It's designed to resist 5,500 pounds, and you could actually just put in 3 bolts rather than 5 or 6. Or sometimes contractors, engineers, they just throw things out. Go, just put in one every 2 feet or every 16 inches. They never actually do any engineering. So if you were to actually engineer something like that, you could just put in 3 bolts and you'd be done. You don't have to worry about anything else. So that's why these, knowing these multipliers, the thicknesses of wood, etc., is so important. So let's go ahead and look at bolts in 2-inch sills. So all the 2-inch sills are made out of redwood. We're not going to find a Douglas fir sill that's made out of. We're not going to find a Douglas fir sill made out of Douglas fir. So in those values, we have a 1/2 inch bolt. It can resist 1,109 pounds. And we just go on down the line. These are all the values that we took our load calculator and we figured out what those are. So we're going to go into these are plates, a URFP. It's a plate that we bolt to the side. It's a bolt substitute, and the exact same thing we have going on here. So it can resist 1,530 pounds. We go into old growth redwood. We multiply that times 0.88, and we end up with a value of 1,346. Now, if you look in the catalog, you're going to see this 1,530 value right here, and that's because all the tests were done in Douglas fir. you have to know to multiply it by these reductions, is what they're called, because of specific gravity. You just have to know how to do that. And if you don't know how to do that, you don't know what that you need to do that, you're going to end up with a retrofit that's not, not what it should be, because, you're using the wrong values for your calculations. So same thing here. We have a URFP as we're 1530, but we're going into the new growth redwood, and we end up with 0.74. The bolt can only resist, the URFP can resist 1132. And we go down here, we have the exact same thing. A UFP, which is the older style, is UFP 10 in the Douglas fir, resists at 1340. We multiply that times 0.88, 1179, and then we go on down here for new growth redwood, and we get 0.74. Now the reason I'm bringing up this part right here is, let's say you're doing a retrofit and you find that there's some UFP 10s in there, and you want to know, well, hey, how strong are the UFP 10s? I want to count those in my retrofit, because you don't want to replace them or waste them. So you just want to know what their value is, and if you take the information here that I'm giving you right now, you'll be able to look at a wall line that's got some existing retrofit work, and you'll be able to say, hey, these UFP 10s can resist this much. I need to add a couple more of this type of hardware to augment it and make it exactly what I want, based on the calculations that I've made. So that's why all this is so important. Now let's go into the shear transfer ties. Exact same thing. Shear transfer ties are all rated in the catalog in terms of pounds that they can resist in Douglas fir. So what we do, we just do the exact same thing. We take our 0.88 multiplier. If we're going into old growth wood, we multiply 0.88 times whatever our Douglas fir value is, and then we end up with this right here. So just an example, Douglas fir for an L90 is 925. We multiply that times 0.88, and we end up with 814. Now, if we're working with a new growth wood, in other words, we look at our Mudsill and it's only 1.5 inches thick, and it's redwood, we have to multiply everything by 0.74, and then we get completely different values. So you see why it's so important. If you don't do this in your retrofit designs, you'll come way off. You won't have the right values for your hardware, and then once you figure out how much earthquake force is going to attack a house, and how strong the retrofit needs to be, if you don't know the strength of your components, you can't possibly do it correctly. So that's why this is also important. There's another type of hardware called an SDS screw made by Simpson StrongTie, and we use those a whole lot, and they are also impacted by specific gravity. So the way these are rated is in terms of the amount of penetration they have into the wood that they're going into. So if you're going into a piece of wood 1.5 inches, you get in 1.5 inches, it will resist 300 pounds of earthquake force. 2 inches, it'll get 450 pounds. 2.25 inches, 550 pounds. Now if we're going into redwood, old growth redwood, we have to use this multiplier again, 0.88. And so for this 300 pounds right here, it's turned into 264. 450 is turned into 396. 550 is turned into 484. So that's the impact of this 0.88. Now, if we were going into new growth redwood, in other words, if it's 1.5 inches thick, and it's sort of a newer house, probably 1945 on or something, made out of redwood, then we'd actually use the other multiplier of 0.74. So it would be reduced even more. So when you're using these SDS screws, a really critical thing to always look at are the end and edge and spacing requirements. First thing I'm going to look at, the most important one, is the edge distance. And so the edge distance, what that means is we're always working with parallel to loading. Just whenever, I'm not going to explain why that is, but it just need to know that. We can be 1 inch from the edge of the thing we're fastening, that the screw is going through. So for example, if you're putting in a 2x4 block in between a couple of studs in a shear wall, for your Mudsill blocking, you want to make sure that the screws, the SDS screws, aren't any closer than 1 inch from the edge of the block. It's pretty simple. You also don't want to have have any of the screws closer than 3 inches from the end of the block, and you don't want them to be any closer than 3 inches apart. So in other words, just to sum up, when you're putting in one of those blocks, make sure it's 1 inch from the edge of the block. Make sure that they are no closer than 3 inches apart, and make sure that you're no closer than 3 inches from the edge, and all these values that we looked at will line up perfectly. You'll get exactly what you need. Now, if you want to learn more about the way we use lags to attach, to use them as shear transfer ties, just please go ahead and hit the card that you see above to your right, and it will take you to the page that discusses how lag screws are used as shear transfer ties. Anyway, I hope this helped you. There's a lot to understand. You probably want to watch this a few times. Put your closed captions on. But it is really important if you want to do a retrofit properly. These are some things that really need to be considered to do a design correctly. And this is also something when you're talking to your engineer or your contractor, you want to say, hey, do you know anything about specific gravity? And they say they don't. You might want to go look for somebody else. Anyway, thanks for listening to me. I hope you enjoyed this video, and if you would like to hear about future videos, please subscribe. You can also email me at info@bayarearetrofit.com and ask me any question you like, and I'll do my best.